Thermodynamics is the study of the effects of work, heat, and energy on a system. It tells us about the energy involved in a reaction and helps us to predict the potential of a reaction. In other words, it allows us to describe the stability of a chemical system and to predict whether or not a reaction would proceed. However, thermodynamics does not tell us anything about the speed at which the change occurs. It will not tell us how fast or how slow the change will happen, only whether a change is likely to happen or not. To delve further into this topic, we need to introduce two types of reactions: spontaneous and non-spontaneous. In thermodynamics, spontaneous means favorable. A favorable scenario is when a system moves from a state of instability to stability, or from a less stable state to a more stable state. Remember, the fact that a reaction is spontaneous does not tell us anything about its speed. It could be fast or slow. A non-spontaneous process is the opposite. This refers to the system moving from a stable state to an unstable or less stable state. In order for a non-spontaneous reaction to proceed forward, it will require the input of energy, such as through heat. Let's try to visualize a spontaneous process by comparing its energy level at the beginning and at the end of a reaction. In thermodynamics, a lower energy state is indicative of a more stable state. At higher energy levels, the system is less stable. A spontaneous reaction moves from the initial state at a higher energy level, which is a less stable state, towards a more stable final state at a lower energy level. The overall direction of the reaction is towards stability. On the other hand, the reaction direction of a non-spontaneous reaction is the opposite. The initial state is at a lower energy and a more stable state, and the reaction direction towards the final higher energy and less stable state is not favorable. The only way to move towards the less stable state is with the input of energy, such as through heat. In order to measure spontaneity, we will use this function. Delta G is equal to delta H minus T delta S. In this equation, G represents the Gibbs free energy, and delta G tells us the total difference in thermodynamic stability between the initial and final states of the reaction in the system. Delta G is dependent on two factors: delta H, the enthalpy factor, and T delta S, the entropy factor. Changes in both of these factors contribute to the overall change in stability. Let's start with enthalpy. The enthalpy factor describes the nature of chemical bonding in the system. It is a measure of how strongly bonded a system is. A strongly bonded system is more stable, has a lower enthalpy, and is indicated by a negative number. The chemical bonds described by enthalpy include both intermolecular and intramolecular bonds. Examples in the order of decreasing strength include covalent, ionic, ion to permanent dipole to permanent dipole, permanent dipole to induced dipole, and induced dipole to induced dipole. As we move from stronger bonds to weaker bonds, the enthalpy becomes more positive. A higher degree of bonding is indicated by a negative number. The second factor contributing to delta G is T delta S, where T is the absolute temperature. S stands for entropy, which describes the motional freedom of a system, meaning how free the various components of a system are to move. The greater the motional freedom of a system, the higher the entropy and the stability of a system. A higher entropy is indicated by a positive number. For example, let's say that a group of people have their shoelaces tied together. Now, each of these people have restricted movement and cannot move independently of each other. So, the system has low entropy and is not very stable. But as we untie the shoelaces, each person can move independently of the others, and thus this system is now increasing in entropy. Eventually, when we untie all the shoelaces, everyone is able to move completely independently of everyone else. Increased freedom of movement leads to greater entropy and greater stability of the system. Motional freedom could be of several types: the freedom to make different kinds of motion, the freedom to move in any direction, or the freedom to move independently of other objects. To return to our equation, note that we call delta G, H, and S state functions, which means that we don't care about the path taken to get from the initial to the final state. We care only about the energy at those initial and final states. So, to figure out these values, we simply subtract the initial state from the final state. Let's visualize these functions. For delta G gives free energy. Let's say that we have a process that starts at a high energy, less stable state, and moves to a state that has less energy and is more stable. Then, G final minus G initial is going to be less than 0. This negative delta G indicates a spontaneous process. Similarly, if we move from stability to instability, a process that requires energy, then our change in G will be positive, indicating a non-spontaneous reaction. Finally, if there is no net change in energy between the initial and final state, meaning that delta G is 0, then the entire system is at equilibrium with no net movement between the initial and the final state. Let's also consider visualizations for delta H and delta S. Note that the sign conventions for delta H and delta S are different. For enthalpy, a lower H value indicates a system that is more strongly bonded. If the final state is more strongly bonded than the initial state, then this results in a negative delta H. The more negative the delta H, the more stable the system, favoring a spontaneous reaction. Higher motional freedom results in a state with higher S. So if the final state of a reaction gains more motional freedom, delta S is positive. The greater the delta S, the more degrees of freedom, favoring a spontaneous reaction. This chart is a good way to practice what you have learned in this module. For each of the scenarios indicated, complete the rest of the outcome by making the best possible prediction. As an example, if delta H is negative, delta S is positive, and T is anything, we can predict that the resulting delta G will be negative, indicating a spontaneous reaction. Now that we have covered the very basics of thermodynamics, we can begin to ask and answer more complex questions, such as how are macromolecules assembled? If we think about it, synthesis of macromolecules like DNA and proteins is really like putting molecules in highly ordered structures, which, as you now know, reduces entropy and restricts movement of a population of molecules. How then do macromolecules assemble into their functional conformation? We also can use our knowledge of thermodynamics to study macromolecular interactions between protein and protein, between protein and DNA, between protein and lipids, and between protein and water.